Okay, so we're going to continue on with Coulomb's law. And what I want to do in this video is do a problem. Let's do an example that uses Coulomb's law that requires us to do some calculations. And in those calculations, we're going to be doing some vector analysis. Okay, so let's jump to the problem and let's get started. Okay, so here's our problem. So we have three charges of equal magnitude. So all these charges in the picture here, the two blue positive charges and that negative charge on the right, all of them have 60 microcoulombs. The red is a negative 60, obviously, because it's a negative charge. Okay, so they are arranged as shown below. What is the magnitude of the electric force acting on the negative charge? Okay, so that's what we want to do. So, I think I think I could fit it here. If I run out of space, I'll jump to the whiteboard and we'll do it there. So the first thing we want to do when we're looking at this is, well, what I like to do is draw a free body diagram of the charge of interest. So which charge are we looking at? Well, if we look at the question, what is the magnitude of the electric force acting on the negative charge? So we are focusing on the negative charge here. And so what I'm going to do is put a, let's see, I'm going to do it in white. I'm going to put a axis here on my negative charge. Okay, and I'm going to draw my forces that this negative charge feels. Now, when we're talking about forces, remember forces are really, they're just another way of representing an interaction. So what's interacting with this negative charge? Well, this negative charge right here is interacting with this positive charge. Okay, so because it's positive and negative, we know that's going to be attractive. Okay, and it's also interacting with the other positive charge. Right? And again, because they're positive and negative, we know they're going to be attractive. So we have two attractive forces acting on this negative charge here. So let me draw these forces out. So we're going to have, let me do this. Let me number this. I'll call this charge 1 here and call this charge 2. And if I do that, then I'm going to draw my forces. I have an attractive force towards 1. So I'll call F1. And then we have an attractive force towards 2. Now, for that attractive force, the direction is going to be really important. Let me draw a line connecting charge 2, the positive charge on top, to the negative charge. So I'll try my best to make it straight, but okay. So that means my charge, my force will be looking something like this. F2. Now, okay, I'm not drawing my forces to scale because I expect F2 to actually be smaller than F1. And the reason why that is because the distance between charge 2 and my negative charge is larger. So that's going to give me a weaker force. The distance between charge 1 and the negative charge is smaller, right? Those two charges are closer together. So that's going to give me a stronger force. So I guess if I wanted to, I could, I guess I do want to because I'm doing it. I will draw my forces. There you go. F2. All right, still not quite in scale, but you get the idea. F1, I expect F1 to be larger than F2. Okay, let's see, what else could I do here? Maybe before I start figuring out what F1 and F2 are, let me just finish this picture here. What I'm missing in this picture is an angle, because I think you see where we're going. It says, what's the magnitude of the electric force? So we're going to have to add up F1 and F2, which means we're going to do components. And if we're going to do components, we're going to need an angle somewhere. So let me define this angle right here. Oops. Theta. Okay, how can I find theta? Well, if you see the triangle there, the 0.60 meters is the opposite side and 1.0 meters is the adjacent side. So if I want to find the angle theta, I could choose tan inverse of my opposite side over the adjacent. Okay, and I just plug that into my calculator. and I get pretty much 31 degrees. Okay. Yeah, 31 degrees there. It's just how to make sure I was actually in degrees and not radians, but I'm good. It's 31 degrees. I guess it wouldn't make sense if it was in radians. Okay, so let's see here. So what was I talking about? So here's F1, F2. We got our angle. Now we want to use this to find our net force. So we have to get a value for the magnitudes. I need to know what F1 is. You know, how much force do I have in F1 alone? How much force do I have with F2? So let me do that off to the side here. So my equation for F, we're using Coulomb's law. K, just actually make an equal sign here. Hey. What the? Oh, I know what. All right. Yeah, F equals K, and I'm just going to be very general here. So Q1, Q2 over R squared, right? That's my equation. So if we're talking about F1, well, K is our constant, so I'm just going to keep it as K. All right, K, you go back to the slide I showed you in the last video, 8.99 times 10 to the 9. Well, actually, I had it in this video too. So 8.99 times 10 to the 9. That's our value for K. Q1, well, the Q1 is 60, right? That's what the problem tells me, 60 microcoulombs. Q2, so Q1 would be this charge down here, right here. So that's Q2, or sorry, here's my Q1. Q2 in this example, we're talking about this charge here. Now, I know it's a little confusing with the notation because say Q1 and Q2. So, well, this is Q1 and this is Q2, but we're not really interested in the interaction between these two, right? Which interactions are we interested in? We're interested in interaction between charge 1 and the red charge, right, this negative charge. And so that's what I'm looking at here. And I'm also interested for, well, anyway, I'm interested in for F1. F1 is between this charge and this charge. So that's what I'm focusing on now. When I do F2, I'm going to look at this charge and this one. Now, I stress that because it's not really too important right now because they're all 60, so it's not really going to change anything. But when you guys do other problems, I'm running out of space. That's, when you guys do other problems, it's going to be important to know which numbers you're actually plugging into your equation. So we're always plugging in the ones, the interaction that we're interested in. So 60 macro, I'm just going to square this. Okay, so 60 microcoulombs squared because both my charges that I'm looking at, the charge 1 and the red charge, are 60 microcoulombs divided by the distance. Well, the distance between the charge 1 and the red charge is 1. Okay, so I plug that into my calculator and I get a number. Now, when you guys plug it into your calculators, don't forget microcoulombs is 10 to the negative 6. So you have to include that in your calculation. So 60 times 10 to the negative 6. I'm going to square that. And 1 squared is just 1. So I get 32.4 newtons. Okay, that's my F1. Now the direction, like I said, like we see in the picture, is in the negative x-axis. Okay, pointing to the negative direction. So we'll keep that in mind for our when we actually do the components. F2. Well, F2 is pretty similar. You have K, your constant, times 60 microcoulombs, and that gets squared. Now, what's the distance between them? Between charge 2, this charge right here, and this charge right here. What's the distance between those two charges? Well, it'll be whatever this hypotenuse is, right? What's that hypotenuse? So we'd have to find the hypotenuse. To find the hypotenuse, you know, you do c squared equals a squared plus b squared, right? So 0.60 squared plus 1.0 squared. And that gives me c squared, right? My distance between those two charges squared. So I'm going to plug that into my calculator. You don't have to take the square root. If you're thinking about how come you didn't take the square root, it's because remember what we're plugging in. Our equation is r squared. So I want to make sure this is my hypotenuse squared. That's why I didn't take the square root, in case you were wondering. So 8.99 times 10 to the 9, that's my k value. 60 times 10 to the negative 6 squared, divided by, then I have that denominator, 0.6 squared plus 1 squared. Okay, and I get 23.8 for my F2. $23.8. Okay, so 32.4 for F1, 23.8 for F2, which makes sense because, like I said earlier, F2 represents a weaker force, right? Those two charges are further apart. So we do expect F2 to be smaller than F1. All right, now that doesn't give us our result, right? We're trying to find out what is that net force acting on that negative charge. So we're gonna have to do a little bit of trig here, a little bit of vector addition. So let me switch over to my to the whiteboard here. And when let me draw this again. So I'm going to draw my axis. All right, something like that. And then I have my two forces, F1 okay, so this is my F1 here. And F2, I already forgot what colors I picked for those. Oops. Okay, so this is my F2 here. And then I have my angle between them, right? So my angle between these two, I think we've calculated 31 degrees. Okay, so if I want to find that force, and I have my values, of course, right? F1 is at, what was that, at 32.4. F2 is the 23.8. Just double check that what I had, yeah. Okay, so we have our values. So we're gonna split this into components here. So I want my X components and Y components for F1, and my X and Y components for F2. And if you saw the video for the components, I like to make these little tables here. So let's look at F1 first. Well, F1's pretty easy. F1 is only on the X component, only on the X axis. So F1 has a negative, what would you say, 32.4? Okay, and then newtons. And then F1, the Y component for F1 is 0. And that's it. That's my F1. Components of F1, done. Let's look at F2. So F2 is going to be a little bit, I mean, there's an angle there, so it just means we have to use sine and cosine. So if we're trying to find the X component of F2, you can see that 31 degrees is adjacent to the X axis. If it's adjacent to the X axis, that means we want to use cosine here. So let me see here. What was the F2 again? F2 was 23.8. And I do cosine of 31. Now, it is 23.8, but it's in the second quadrant, right? So if it's in the second quadrant, you gotta put a negative there. Let me make this a little bit neater. Okay, so 23.8 cosine 31. And then what would be the Y component? Well, the Y component will be 23.8 sine 31. And you can see in the picture, it's in the second quadrant, so that means a positive Y axis. Okay, so there's my F1, F2. I'm gonna add these together to get my F net, my net force here. I could put little things here. Okay, so to get my net force, I'm just gonna add these two numbers. So 32.4, what did I actually say, negative 32.4. 32.4 minus 23.8 times cosine of my angle. Okay, so I'm getting a negative 52.8. Okay, now my final answer, if you're wondering about sig figs here, my final answer is only going to have 2 sig figs because that's the numbers our problem gave us was 2 sig figs. So if you go through all that vector or all the sig fig rules, you end up with 2 sig figs at the end. But I'm keeping an extra one just to avoid rounding errors. And then 23.8 times sine of 31 for my y-axis. I get 12.3. Okay, so last step here. Find the magnitude of f net. We just take the square root of that 52.8 squared plus 12.3 squared. And that gives me our final answer. So square root 52.8 squared. One second. Plus the 12.3 squared. All right, so you get 54. All right, that's my answer. Okay, so we had to use Coulomb's law at first, and using Coulomb's law goes by pretty quickly. And then we switch over and start doing vector addition, and that's pretty typical for these examples. So let's go back here to make sure I answer the question. So what is the magnitude of the electric force acting on the negative charge? Well, there are 2 electric forces, so we had to find the net force, and we ultimately found a net force of 54 newtons. Okay, so that's an example of Coulomb's law, and we're gonna. I mean, we should do vector addition a lot when it comes to Coulomb's law, and we're going to talk about the electric field next. Let's see here in the next couple slides. And electric field is very, very similar. We do a lot of vector addition for that electric field. Okay, I put this in here because that was pretty interesting. That if you look at DNA. The TA and the GC bases, they have a certain configuration so that they are attracted to each other based on Coulomb's law. So it's kind of interesting to see Coulomb's law application there in something biological, that you have like a lot of an attractive force and repulsive force between the nitrogens, oxygens, and carbons. Actually, oh, sorry, hydrogen, nitrogen, and oxygen. Okay, so just want to show you that. Just I always thought it was interesting. All right, so we're gonna next lecture we'll talk about electric fields, and chapter 22 introduces us to electric fields. We really dive in deeper with electric fields in chapter 23. So we'll do that next lecture.